All right, so chapter 5, as I said, we're going to look at the last two kinds of functions that we have not done, exponentials and logs. And we're going to do the same thing with them that we do with every other function. We're going to look at how to solve some equations of those kind. We're going to graph them, and we'll look at transformations, shifting up and down, left and right. Same transformations we always do every time. All right, so first I just want to graph the difference between a polynomial and an exponential. Bless you. Nice. Okay. What's on the left between these two functions, x to the second power, that's a polynomial. What's on the right is an exponential. In each case, you have a base and an exponent. But it's what's in the base and what's in the exponent that kind of controls what kind of function it is. Let's look at this one first. For the one that I just put a box around, what's the base there? It's an x, and even more general, it's just a variable. Okay, the base is a variable. And what's the exponent? It's a 2. Okay, it's a number. Now, for the one that I just circled in blue, what's the base there? That's a base, that's a number. Okay? And what do we have in the exponent? We have a variable. Okay? So that's the difference. One of them has a base that's a number, the other one has a base that's a variable. Same thing for the exponent. One of the exponents is a number, one is a variable. When you have something that looks like that one, the one I just put a box around, that is an exponential expression. The one on the left, that's a polynomial. Specifically, it's a quadratic expression. It's not a quadratic equation. To have an equation, it needs to have a what? It has to have an equal sign. These aren't equations, they're just expressions, okay, because they don't have equal signs. All right, and did I say we were going to graph them? No. Okay, I will do some graphs in a little bit. Okay. Also, think about if x is, let's say, make up a number, 20. Okay. If you plug in 20 for x here, you get 20 squared. What's 20 times 20? 400. You get 400. Okay, so it's pretty big. Now let's plug in 20 for the one on the right. 2 to the 20th power. Do you think it's going to be bigger or smaller than 400? Yeah, it's going to be a lot bigger. So it's in the millions.
1,048,576.
Yeah, it's a big difference. So the key thing with an exponential is it gets a lot bigger, a lot faster. Okay? Very, very big. Okay? Maybe not for small values of x, but once you start getting like 10, 15, 20, keep going up, this one's going to get a lot bigger, a lot faster. So the one on the left, okay, that's where the variable is in the base, and the exponent is a non-negative integer. That's a polynomial. X squared, 2x cubed, 5y to the 4th power. Those are all examples of polynomials. You have a variable in the base, and you have an exponent that's not negative, and it's not a decimal. We've studied those back in chapters 2 and 3. Okay, what we're going to look at is the one that's on the right. That's when the variable is an exponent, and the base can be any positive real number except 1. That's called an exponential function. That's an exponential function. Okay, this is also an exponential function. As long as the base is a positive number, both of those are positive, and it has to be, and it can't be 1. Why do you think this would be exponential? Y equals 1 to the x. Yeah.
There's 1 times itself, it's just 1.
Right. This is just basically graphing a horizontal line at 1. Okay, 1 to any power is always 1. That's a constant function. That's not exponential. But these two are. One of them is an example of exponential growth. The other one is an example of exponential, anyone know the other word? Decay. And whether it's going to be an exponential growth or decay is controlled by the base. Yeah.
So if 1 to the x isn't an exponential, then does that mean that 0 to the x is also not an exponential?
Yeah, 0 to the x would not be an exponential. Yeah, that would be because 0 to any power is always 1. So that would just be like, yeah, that would also be like a constant function. Yep.
Would x to the x be exponential?
No. No, x to the x would not be exponential. I'm not really sure what it would be called, but it's definitely not exponential because it has to have a base that's a number to be exponential. Yeah.
You said 0 to any exponent is 1, but isn't it also...
Except 0 to the 0. If you type in, let's see, 0. Oh no, I think that's actually, no, that is an error. Yeah.
Okay, and also,
Yeah.
is it also any number to the 0 power? Is that also 1?
0, so 0 to any power,
Or,
I'm sorry, 0 to any power is 0. That's what I meant to say.
Isn't a number to the 0th power just the number?
Well, a number to the 0th power is different than what I have on the calculator there. That's, yeah, so 0 to any power is 0. But then, if you take like 5 to the 0,
That's 1, right?
that's 1.
Yeah.
Yeah. A number to the 0 power is always 1. Does that make sense?
Yeah, that's what I was saying.
Okay, yeah. So these are both examples of exponential functions. Yeah, or actually those are exponential equations.
So for the second equation,
Mm.
that's exponential, not radical? Or is it radical and exponential?
No, it's nothing to do with radical because that 1/2 is
Not radical,
in the
sorry.
exponent.
The division one.
Oh, rational?
Rational.
No, rationals can't have variable exponents. Yeah.
So it's
No.
only when it's a variable exponent, it's exponential.
Variable exponent and the base is a positive real number, not 1.
Alright.
Yeah. This is not exponential because the base is not a positive number. It has to be positive. In fact, if you try to graph that on the calculator, it won't even work. You can't graph it. I'm not going to really get into why, but you can't. You can't do it. Okay, so let's graph an exponential. Let's put in. You can put in any number to the x. Okay, I'm going to do 2 to the x. I'm going to do zoom 6. And that's what an exponential growth function looks like. All right, let's look at that a little more. How far left and right does it look like that graph is going to go? Yeah, it's going to keep going left forever. It's going to keep going right forever. It starts to go up more than to the right, but it is still going to slowly go to the right. How about up and down? Does it go up and down forever?
No. It just goes up forever.
It does go up forever, and it starts to come down, and it gets close to a number, but it never reaches it.
0.
Yeah, gets close to 0. Because remember, I graphed this. I graphed 2 to the x. If x is -1, bless you. What does 2 to the -1 mean? If you do that out, what is 2 to the -1?
0.5.
0.5. Yeah. It means 1 over 2 to the 1. So when you're at -1, you're at a half. How about 2 to the -2?
Yeah, wouldn't that be 1/4?
1/4, yeah, 0.25. So what happens is the more and more negative you make the exponent, the bigger the denominator gets, the smaller the whole fraction gets. So the next, like 2 to the negative third would be 1/8. 2 to the negative fourth would be 1/16. So it's going to keep dividing by a bigger number. But if you divide 1 by something bigger and bigger, does it ever hit 0? No, it just gets very small. So that's what's happening as you head to the left. It gets close to 0. And what do we call that again when you get close to something but you don't reach it?
An asymptote.
It's an asymptote. Yep. So domain, all real numbers. And remember, I'm just reminding you again here that the base has to be a positive real number except the number 1. We already wrote that down on the other page.
You have really good handwriting. Jeez.
What's that?
That's really good handwriting.
Oh, yeah, I don't usually write that good, huh? No, okay. Okay, so those are all examples of exponential functions. Okay, 10 to the x, 4 to the v, and pi to the x. Okay, so there's only 2 things you have to check to make sure it's exponential. 1, is the base a positive number that's not the number 1? Yes, yes, yep. And you have a letter in the exponent? Yes. So those are exponentials. These are not exponentials. The first one is a polynomial. That's a cubic polynomial, x cubed. This one you could also think of, instead of dividing by 2, you could think of it as a 1/2 in front. That's a quartic polynomial, 1/2 x to the 4th. The last one doesn't really fit in the category. It's a combination of a radical and a rational function. But it's not exponential.
So if this is a variable at all, so if it's 10 raised to the 4x, that's still an exponential function?
Oh yeah. Yep. Because, I'll talk more about that, but yeah. If you had, just to do it a little simpler, if you had 10 to the 2x, that really means this. Because remember the rule, when you have a power to a power, what do you do with the 2 things when you have powers raised to powers? You multiply them. So if you multiply 2 times x, you must have had 10 to the 2 to the x, and then what's 10 squared? 100. So you can really write it exactly like I said. 10 to the 2x is exactly the same as 100 to the 1x. It's the same thing. We'll talk more about it. Okay, so let's graph these two. Y to the 2x and y to the 3x. Does anyone have a guess what the difference will be between the two? They're both exponential. But what do you think the difference with the 3x is going to be?
Is it going to get there faster?
Yeah, the 3x gets bigger faster. So the 3x is going to curve inside of the 2x. It's going to curve up faster. You won't notice it on the left side. But then once you get past the y-axis, you can see it's curving up faster sooner. That's it. Any question on the difference between the two? Yeah?
Do those lines ever intersect?
Yes, they do. Yeah, they do cross. I can show you better here. They cross at 0, 1. Yep. In fact, if I just keep drawing different exponentials, they all go through the point 0, 1. As long as you don't shift. Now, if I do something like, say I do 2x, and then I do a plus 1, and I do 3x, and a plus 1, that plus 1 is a vertical shift up 1. Okay, so what that's going to do is it's going to shift them both up 1. Now they're going to cross at 0, 2. They're both going to go right through that one. Okay, but yes, if you do graph 2 exponential functions with the same base, with different bases, they should cross somewhere. Yeah. question on that? Okay, so sometimes we're going to have some exponentials that have a negative in the exponent. We don't want to have a negative in the exponent. Okay, negative in the exponent is going to make it hard to work with. So we kind of just said this earlier. But what is a to the negative 1? If you wanted to write it without a negative 1 exponent and do it as a fraction. It means what?
A over 2.
A over 2? Like that?
Be just 1 over.
Just 1 over what?
A.
Yeah. So a to the negative 1 means 1 over a. Okay, so now let's use that fact. We're using to the negative 1 power, just means to flip it. Okay. Let's figure out what this would be. Now that's exponential, okay, as long as the base is a number that's positive and not 1. But this negative is going to mess us up. So we don't want to have this negative here. What number is in front of the x, even though it's not written? Right, negative 1. So it's like having this. It's really like negative 1. And what operation are we doing between the negative 1 and the x? We're multiplying. Now, when we just said it earlier, but when do you multiply two things together and put the answer in the exponent? Like, what would you have had before this step that would cause you to multiply a negative 1 and an x together? Yep.
E to the power of negative 1 to the power of x.
Right, you would have had a power raised to a power. So a to the negative 1 to the x. Now, if you were going to simplify it, you multiply negative 1 times x together. But this, we can now get rid of the negative exponent because we just said what that is. What's a to the negative 1?
1 over a.
It's 1 over a. So to get rid of a negative exponent, you change that into that. So let's say I gave you 2 to the negative x. What would that turn into so that this negative goes away? Yeah.
Half to the x.
Yeah, 1/2 to the x. How about if I had 4 to the negative x?
1/4 to the x.
1/4 to the x. And the point is, when you look at that, you might think, oh, 4 to the negative x, I have a base bigger than 1. It's a 4. That's not really a 4. It's really a 1/4. Okay? So when you have a negative exponent, we have to get rid of it like that so that we can look at the base clearly. This negative messes it up.
If you think about it, it makes sense because it flips the chart.
Yeah, it flips it. Yes, this negative is a horizontal reflection. So if you think about what a horizontal reflection would look like, well, that's growth. If you mirror image that, it's going to look more like this, and it's going to turn into decay. And that's exactly what decay is. When you have a base smaller than 1, that's when your graph goes down instead of going up. We're going to write that down. Okay, so let's look at these two graphs. If you look at them quick, you might say, oh, they both have a base of 2. They're both exponential growth. No. The top one has a base of 2. But what's g of x, really? 1/2 to the power of x. So now looking at that, since the base is less than 1, g of x is really decay. So I kind of already showed you what it's going to look like. It's going to look like the horizontal reflection, but I'll show you on the calculator. Okay, so let's put in 2 to the x. And for the purpose of graphing it, you could put in either one, okay, when you're graphing it. That doesn't make a difference. So 2 to the negative x. Okay, so there's 2 to the x. That's your exponential growth. And 2 to the negative x, it's going to be in red. And it's going to come down. And it's going to be a mirror image of what's in blue. So the blue one is called growth, and the red one is decay. Any question on that? So as far as a window, because we were finding a complete graph, the standard window is fine. It shows you everything you need to see. Yeah.
Which one is which?
So the let me just let's put this here. Okay, so the blue one is 2 to the x. And the red one is 2 to the negative x. Okay, let's start with the domain. They each have the same domain. What's the domain of both of them? Yeah, negative infinity to infinity. The domain is all real numbers. Every exponential function has a domain of all real numbers. Okay, all of them. Yeah, every single one. Yep. If it doesn't have a domain of all real numbers, then it's not an exponential function. So that's the domain for both. Now, how about the range? We already talked about the range for the blue one earlier. How does the range of the red one compare to the blue one? Yeah?
This is just a question about range in general. Would it never be 0 because it has to be greater than 0 for it to decay, or for it to...
Yeah, it has to decay to something. There has to be a value it's
So
getting
it'll
close
never
to.
approach 0, or it'll never get to 0, right?
It will never get to 0 in this case. Correct.
So does that mean the range is greater than 0?
Greater than 0 up to
Infinity?
infinity on both of them. Yep. So the range greater than 0 to infinity. Now the domain you can't change, no matter what you do. The range you can. Okay, I showed you an example earlier when I did a +1 and you shifted it up. So you can change the range. Okay, any question on that? Now that was for 2 to the x and 2 to the negative x. But if I did 3 to the x and 3 to the negative x, it would have been the exact same chart. 5 to the x, 10 to the x. Wouldn't have made a difference what base I used. And that's what we're going to look at on the next page. So instead of thinking specifically about 2 to the x and 1/2 to the x, we're going to think about anything to the x. 2 to the x, 3 to the x, 5 to the x. And then the same thing flipped. So f of x is going to represent some type of growth. G of x is going to represent decay. Now what I'm asking here is pretty much the same thing as domain and range. Okay, the first one says, looking at f of x, okay, so that's the one that looks like our blue one. If it was 3 to the x, it would just curve up a little sooner, but it still is going to look something like the blue one. As x heads to the right, the y value is getting close to what on the blue graph? As x heads to the right, what does the y value? It goes to positive infinity. Yep. And still looking at the blue graph, as x heads to negative infinity. Where's negative infinity? That's to the left. So as x heads to the left, what happens to the y value on the blue graph? It approaches 0. Yep. Now for g of x is when you have a fraction to a power. Could be 1/2 to the x, 1/3 to the x, 1/10 to the x. Doesn't matter. It's going to look something like the graph in red. So on the red graph, as you head to the right, what does your y value get close to? It gets close to 0. And again, on the red graph, as you head to the left, what does your y value get close to?
Infinity.
Infinity. Yep. So that's basically summarizing all exponential growth and decay graphs. One side approaches 0, one side approaches infinity. And you might think, well, what if you flip it? Well, if you flip it left to right, that won't change. You'll still have a 0 and an infinity, but if you flip it vertically, okay, then it could change. If I put, instead of putting a negative in the exponent, if I put a negative in front, that's a vertical reflection. Instead of approaching infinity now, if it flips vertically, what do you think it's going to approach? Right. So before, it curved up. You're going to see it in a second. Now it's curving down. Still exponential, but it's a mirror image of an exponential growth graph.
Mr. Hager, how did you put on the calculator the negative in front of that was equal to 2?
The negative,
Yeah.
I put it in front of the 2.
Yeah.
So the 2, the negative is not being raised to the x power.
No, like.
Oh, how did I insert it?
Yeah.
I did second insert and then press negative.
Oh, thanks.
Now that would be positive. And that'd be negative.
Babe, isn't that not an exponential function?
With all those negatives?
Well,
No, it's, well, as long as it's, when I do this, just be careful. The base is a 2. Kind of think of it like this if it's clearer. The base is a 2, and the exponent is an x. The negative is in front of the base. I think with the parentheses it looks clearer now. Yeah.
So what exactly is the difference between a non-negative base and what you're showing us currently?
What I'm showing you right now, that is a non-negative base. The base is 2. This is just exponential growth and then reflected. Putting a negative in front causes a vertical reflection. Same with every other function. Like if you graph square root of x and then negative square root of x, they're just vertical reflections of each other. Okay, but still considered exponential. It's just a mirror image.
You can't do parentheses, -2, parentheses to the power of x, right?
You can't do, can you say that again?
Parentheses, -2, parentheses, power of x.
Parenthesis, no.
Right, that would be the negative.
Isn't
You cannot do that.
it the
It's in the parentheses.
Yeah, there's a big difference here. One, the negative is inside, one, it's outside.
would you just take the negative out and it'd be the same thing?
No, these are not the same thing. Those are completely different.
Why can't you take the negative out?
Well, if you take it out, you're changing the problem. It's different whether it's inside or outside.
Is it?
Well, yeah. Think of like this compared to this. This means to multiply 2 times itself 3 times and then throw a negative in front when you're done.
But couldn't you just change that one to -1 times 2 to the third?
Well, let me finish this and show you. So this might be why you think they could be the same, because this means to multiply -2 times -2 times -2, and in that case they do come out the same. Now try it with this. Let's try it to the 4th power. So this means multiply 2 times itself 4 times, and then throw a negative in front. What's 2 to the 4th?
16.
And then throw a negative in front when you're done.
-16.
That's -16. This means multiply -2 times -2 times -2 times -2. That's 60. So they might come out the same for some exponents, but not all the time.
And why can't you just take out the -1?
Take out what here?
So on the bottom one, why can't you just rewrite that as -1 times 2 to the 4th?
Well, that's the top one.
But isn't that the bottom one? Can you
No.
just
No, because it's not
They're not the same.
multiplying -1 by the exponent. It's just multiplying by the base.
You cannot take this negative out in front. If you do, it's a different problem.
Why?
Because you get different answers.
If you graph that, would it be like this?
This I can't even graph this and show you.
Really?
No, I can't graph a negative
I
base.
thought it would be like a zigzag.
It would be like a zigzag, but it doesn't even do that.
Oh,
Yeah,
that's lame.
yeah. Yeah, if you put the negative out in front here, the answer is -16. If you put the negative inside, it's +16. So that proves they are not the same thing. If you have the negative outside or inside, they are different.
What's your late day?
Thursday.
All right.
Yeah.
Buckle up for Thursday.
Yeah, they're not the same thing.
I'm still not getting it. I'm not going to waste the time. So.
If you hit graph right now, you're not going to see anything in red because the red one is the one that has a negative base raised to a power. Doesn't even show up on the screen because it can't graph it. So even if you just look at them graphically, one of them shows up, one of them doesn't even show up because you can't graph it. So the key difference, whether a graph is going to go and curve up to the right, like that, or it's going to curve down to the right, is whether the base is bigger than 1 or between 0 and 1. If it's bigger than 1, that's called exponential growth. If the base is between 0 and 1, that's decay. The closer the base gets to 0, the faster it will decay. Right, so this would be, let's see. Here's an example of something that decays very slowly versus something that decays sharper. So the rate of decay is controlled by the base. Closer to 0, sharper decay. If it was close to 1, let's say you had a base of 0.9, it's going to decay, but it's going to decay very slowly. Very slowly. So any question on the difference between when the base is growth versus decay? What if the base is a negative? Then what?
It's not an exponential.
It's not even an exponential function. We don't even talk about that. Yeah, it's not. All right, transformations. So transformations, and now we'll talk more about like the reflection I was doing earlier, work exactly the same as every function we've done all year. So let's say y equals. You have a base. Could be any base you want. Let's do bx plus a times c plus d. The a, the b, the c, and the d do the standard transformations that we're used to. The a and the b are inside the exponent. Those are going to be your horizontal. The c and the d are outside. Those are our verticals. Let's start with a. What do you think a would do? Adding or subtracting inside the exponent? Yeah, it's a horizontal shift. How about b? What do you think b would do? It's still inside the exponent?
Would this be a horizontal stretch?
Right, it's a horizontal stretch or compression, yep. And remember, a and b are backwards. So if you make a positive, it's going to move it to the left, and negative would move it right. The bigger you make b, the more compressed the graph gets. So like if you do this, 2 to the 5x That's a horizontal compression by 5. If you wanted to stretch it by 5, you'd have to do this. That's a small number, 1/5, so it would stretch it 5 times as much. So this is a stretch by 5. This is a compression by 5. And so it's backwards. It's not what you would think. How about C? It's multiplication like B, but now it's on the outside. Yep. And that one is not backwards. If you make C a big number, like 50, that's a vertical stretch by 50. If you make C a small number, like 1/3, that's a stretch by 1/3.
This is also where reflections take place, right?
Yes, if the B or the C are negative, you get reflections. If B is negative, that's a horizontal reflection. If C is negative, it's a vertical reflection. And how about D?
Vertical shift.
Right, that's a vertical shift. And is that one backwards or no?
No.
No.
Wait,
Po-
so
positive is up, negative is down.
negative C is a what reflection?
If you put a negative for C, that's a vertical reflection.
So, like,
You could also say over the x-axis. If B is negative, that's a horizontal reflection. That's over the y-axis.
This might be a silly question, but can there be a negative B?
Yeah, that would be a horizontal reflection with a stretch or compression. So if you've got something like this, you got two things going on. You've got a horizontal compression by 4, and you have a horizontal reflection. So yeah, two things. All right, so let's try a few examples. So list the, I think it said transformations. List the transformations. So when you do transformations, you're always going to be describing something with the same base to something with the same base. So you're going to be comparing a 3 to the x and a 3 to the something. You'd never compare like a 4 to the x to a 3 to the x. Can't do that. Okay, you got to have the same base. Okay. So how many transformations are happening in g of x? There are 3. Yep. You do have to list them in the correct order, and the order is alphabetical with the letters I used. A, B, C, and D. If you don't have one of the letters, skip. Okay, do we have a value in the spot for A?
Yes.
Yes, what's the value?
1.
Yeah, it's a +1. What's a +1 going to do in the A spot?
Horizontal shift right.
Shift, you said which way?
Right.
Left. Positive moves it left. Okay, do we have anything in the spot for B? No. And I guess if you want, you can think of having a 1x there, but there's no horizontal stretch or compression. Okay, do we have anything in the spot for C? Yep. And what's in the C spot?
Vertical stretch by factor 2.
Yep, so we've got a 2, which means it's a vertical stretch by a factor of 2. Let's see. Do we have anything in the spot for D? Yep. What's in the spot that's D?
vertical shift down 5.
So that's going to shift down 5. And so when I ask you to describe the transformations, that's what I mean. Any question on that?
You go back.
We're not going to do. We're going to talk more about that thing that's on the next screen tomorrow. Let's see. So that has to do with the number e, which is a number in math dealing with logarithms. We'll talk about e tomorrow. Okay, so last thing we're going to look at is what is the formula for exponential growth? Okay, what does it look like? That's the formula for exponential growth. It's P times 1 plus R to the T. What makes something exponential growth is it has to increase by a percentage. So if I said to you the population of a town is going up 5% every year, that's exponential. If I said the population of a town is going up by 50 people every year, that's linear. Just adding 50. That's all you're doing. But if you increase or decrease by a percentage, that will be exponential. So when they give us a rate, it's usually going to be as a percentage. We need to always make sure we change it to a decimal. So, like what's 12% if you make it a decimal? 0.12. Always have to use the decimal. So P is the initial amount. Could be an initial amount of people, an initial amount of, initial amount of money, but it's some starting value. R is your growth rate, and T is time. Now, if you change one thing in that formula, it becomes decay. Anyone have a guess what would change to make it decay? Yep.
1 minus.
Right, it becomes 1 minus R. So if you said you have a decay rate of 5%, that means the population is decreasing 5% every year. Okay, there's two special types of growth and decay. One type of growth we're going to look at is doubling. Okay. Another kind of exponential decay we're going to look at is halving, something being cut in half each time. Okay, that's called half-life. So we'll look at just a kind of generic growth and decay problem, and then we'll look at a special one that's doubling and a special one that's halving. But it still is going to use these two formulas every time. The P, the R, and the T are the same thing in the decay as they are in the growth. All right. So first thing we have to figure out is if this is growth or decay. By reading that first sentence, you should be able to tell. What do you think? Yes?
It's increasing, so it's growth.
It's growth, yep. And it's not increasing by a certain amount of people every year. It's increasing by a certain percent. That makes it growth. So the first thing they want us to do is write an equation that models that, and then graph it, and figure out when we hit 100,000 people. Another way they could ask this question is find out how long it takes for the population to double. That's what's happening. The population is double. Okay, so let's start with the formula. So I'm going to use P of T, where P is population and T is time. So for exponential growth, what comes right after the equal sign? P, which is the
Initial
amount. Yep. What's our initial population?
Okay.
So 50,000 times. And what was inside the parentheses?
1 plus 3.
So 1 plus our rate. Well, it's 2.5%.
0.025.
0.025. And the last thing I need, and this is what makes it exponential.
raised to t.
Yeah, I need my variable in the exponent. Okay, we do want to simplify that. What's in the parentheses? 50,000. And just make it 1.025. Okay, so there's your function. Now we're going to graph it. Okay. All right. So when we graph it, I'm going to type it in on Y1. 50,000. Remember, you always have to use X as the variable when you type it in. Okay, what's the minimum amount of people we're going to have?
50,000.
Right, it's going to be 50,000. It's only going to grow from there. And we want to find out when it grows to what?
100,000.
100,000, so let's do 110. Now, X is time. What's the smallest amount of years that can go by? 0. Now, we don't know how many years it's going to take to hit 100,000. Let's assume it happens within 35 years. If I can't see my graph hit 100,000, I'll have to set X bigger. Okay, so there's my population. Yeah, I think we're okay. Yeah. Okay, and we want to see when that population hits 100,000. So what else am I going to do on the calculator to find that?
Set y equals 100,000.
Yeah, we're going to do another y equals. I'm going to put in 100,000. Hit graph. All right, so I can see where it hits it. How do I find where it hits it? Yep. So second calc, intersect. Does the guess matter?
No.
No. So just pick a point on the blue, red, and hit enter. Okay. So how long is it going to take?
28.07 years.
Yeah, it's going to take about 28.07 years for the population to double. And I use the squiggly equal sign because that's approximate.
You should always use an approximate when rounding, right?
Yeah, anytime you round, you should really be using that symbol because it's not exactly 28.07.
Should we say years after?
Yeah, I should throw years in there. 28.07 years. Yep. Question on that one? Okay, so anytime you're graphing, be careful about including negatives. A lot of the time, negatives won't make sense, especially if you're dealing with an amount of people. That can't be negative unless it's k. Then it, well, I guess it can only go to 0 though. Can't go negative even into k. And also in time, you can't have negative time. You can have 0 years, 2 years, 3 years, but you can't go back. Okay. All right. Now let's think about something double. Okay. Doubling is still exponential growth. But what do you think the percent is if something is doubling? What do you think the increase is? Yeah?
200%?
200% would be triple.
100%.
It's 100%. Okay? Because you're taking what you already have, and if you increase it by 100%, it will double. So if you take the number 10, so take the number 10, and you increase and you add to that 100%. Well, what's 100% of the number 10? 10. So if you add 100% to what you already had, you just doubled. Right? What's 100% as a decimal? 1. So what do you think is going to be inside here? A 2. Yep. If you make that specifically a 2, that's the formula for something doubling.
Mr. Hager, is there a reason why 100 is all of something, or did we just make that up?
Why what?
100 is all of something?
Because we're base 10.
Yeah, so we just made it up.
It's like time.
It's
Like
like
if you
something
have a
meters.
full foot, that's 12 inches, but we decided that 12 inches equals 1 foot.
Yeah, 100% is just the number used to represent a whole.
So there's nothing special about 100.
No, we could have used a different number, I guess.
Like 360.
But we don't.
Could have used that.
Like on a circle for angles, 360 represents the whole. It's not 100 degrees in a full circle, it's 360. That's just the number they picked that represents going all the way around.
It's the number of divisions that you've decided will make up a whole.
So this is the exponential growth formula again, the initial amount, except I didn't put 1 plus r. I put 1 plus 1, which is 100% growth. And the exponent, we just have to be careful. It is t, but you have to divide by the length of the time it takes to double. Because the exponent is really the number of doubling cycles. That's what the exponent should be. So let's say something doubled every 3 hours, and 12 hours have gone by. How many times would it have doubled?
4.
It would have doubled 4 times. That's what the exponent needs to be. It would have to be a 4 in that case. If 12 hours go by, it hasn't doubled 12 times. Okay, whatever you make that exponent, that's how many times you're saying it has doubled. Now, if it doubles every hour, then yeah, 12 hours, 12 times it would have doubled. But if it doubles every 3 hours, after 12 hours, 12 divided by 3, it has doubled 4 times. I just made up 3 hours. All right, let's try an example. So we got 100 bacteria. And let's say that it doubles every 3 hours. I want to know when we will have 350,000. So we'll write our bacteria as a function of time. Okay, how many bacteria are we starting with? 100. And since we're dealing with doubling, they don't have to tell us the growth rate. Doubling tells you that. What do we always put in parentheses when it's doubling? We always put a 2, because that's 100% growth. So it's 1 plus 1. And what's my exponent going to be?
3. Oh, no.
X divided by 3.
Yeah, so when we type it in on the calculator, we'll use x. There's your formula. All right, let's type that in and see what happens. So you might think it's going to take a long time because you're only starting with 100 and you're trying to get all the way to 350,000. But doubling, things happen pretty quick. So 100 times 2. And we'll put x divided by 3. And we want to know when that hits how much?
350,000.
350,000. Okay. So what's a good value for the minimum amount of time that can go by?
0.
0. Yep. So we could have 0. And 35 is hours. Let's go up to 60 hours. Okay, so just under 3 days. 60 hours. Well, two and a half days. All right. Why min? What's the smallest amount of bacteria that we have?
100.
And we want to know when we hit 350,000. So let's go to 400,000. So the growth of the bacteria starts off kind of slow, but then it takes off. So I did 60 hours. That's 2.5 days. It's going to happen in way less time. How do I figure out where they cross?
Intersect.
So we'll do intersect. Okay, so if you start with 100 bacteria and it doubles every 3 hours, in just over 35 hours, it will hit 350,000. Okay, so time is about 35.32 hours. And then within another 6 hours, it'll double 2 more times, and then it'll already be in the millions. Right. Question on that?
Can you show me what you put into the calculator again?
For the y equals? Yep.
Okay. Thank you.
Okay. Any other questions on that? Okay, so that's growth. Let's try one where we have decay, and specifically we're going to look at a decay that's called half-life. So half-life is generally used for like radioactive material, and it measures the amount of time it takes for half of the radioactive material to decay and no longer be radioactive. So if you start with like 1,000 pounds of radioactive waste today, and let's say the half-life was 100 years. After 100 years, if you start with 1,000, then you'll have 500 left. After another 100 years, or whatever I said, then you have half of that. After another 100 years, half of that. So what does that really mean about the amount you have left over time? It gets close to what? But does it ever reach it? No. It never really completely goes away. It just gets closer to zero. Some things have a half-life of a very, very short amount of time. Could be measured in like milliseconds or microseconds, very, very short. Other things have half-lives of years. That's why, like in Chernobyl, there's still radioactivity there because it's going to take hundreds of years, maybe thousands of years before it's all gone. It'll take a long time. And you can probably guess by the formula, but when we did decay, it was 1 minus r in parentheses. What do you think the percent is if something is getting cut in half each time?
Negative 100.
This could be 50%.
Well, it's still a positive number. It's just decaying at the number, not increasing at the number. Yeah? It's a 50% decay rate. Yep. If something decays at 50%, that's half. That's half. What's 50% as a decimal? 0.5. Normally in parentheses you have 1 minus r, but what's 1 minus 0.5? 0.5. That's where the 0.5 comes from. It's really 1 minus r, where r is 50%. All right, so we'll try this one, and then that's it. Okay, so we have a 5-gram sample of something that's radioactive, and the half-life is 20 days. And let's say as long as it's under 1 gram, then it's safe to be around. I want to know, when will it be under 1 gram left? How long is that going to take? And you kind of estimate it. After 20 days, you're going to have 2.5. After another 20 days, you're going to have 1.25. So it's, and then once you get half of that, you're going to be under 1. So it's somewhere between 40 and 60 days. Well, let's see if we can figure it out. Right, so let's write it as an equation. So I'll do A this time for the amount that I have left. All right, how much did we start with?
20 grams.
How many grams?
5 grams.
Yep, 5 grams. And when you're doing half-life, what always goes into parentheses? You always put a half. Remember, it's really 1 minus r, but r is 50%. And what's my exponent going to be? Yeah? T over 20. Okay, so there's an algebraic representation, and now let's graph it. Okay, so we need 5 Just so I don't have to do another fraction, instead of 1 over 2 in parentheses, I'm going to do 0.5. Okay. Since this is decaying, what's the largest amount of material that we're going to have? 5. And what's the smallest that it's going to get close to? It's going to get close to 0. So let's go 5 grams down to 0. And we're going to look it up to 60 days. So that'd be 3 half-lives. I just put something in wrong. Yeah, what did I put in wrong?
You made the line in 5.
Yeah, I need to switch that. 0 and 5. Okay, so there's our sample. Decaying. They're going to ask us when it's under 1. And that's going to be the question. Does it go far enough to the right to be able to see where it's below 1?
Yeah.
Yeah, I think it does. Okay, so when is there less than 1 gram? So first thing is figure out when you have exactly 1 gram. Put in 1. Right, and then we're going to calculate the
Intercept.
We're going to find the intercept. Now he's got to be careful because that's not the answer. The question is not when do you hit exactly 1 gram. The question is when do you have less than 1 gram.
Can we just do less than 46 days?
So you think if we go less than 46 days, we'll have less than 1
greater
gram?
than.
Greater than, yes. Because the further you go, the more it decays. So any time after 46.4 days, time has to be greater than 46.4 days. Any question on it? Yeah.
Is there a way to represent an estimation of greater than or less than? Because obviously the squiggly lines for equals, but
So it's squiggly arrow.
Oh yeah, no, I've never seen anything like that. No. Yeah. A good question, but no, I've never seen that. I guess the only thing you could do here is just write like approximately under it. Right. So that's 5.1, and that's everything on exponentials. Tomorrow and Wednesday we'll do logarithms, and I may split Wednesday into 2 days so we can just slow down a little bit. Yeah.
Are you fine with just the t is greater than 46.4? Do you also want the approximately to?
You could just write t is greater than 46.4.
Then that's fine.
Yeah. Yep. Okay, so that's the homework for tonight, 4 through 7. 1925, 2731. 35, and then 47 to 49 and 57.
Some of those
I think it's
talk
like
about
13
users
questions
number.
maybe.
Some of those talk about users number one that you said that you could go over tomorrow.
Oh, well, okay, let me take a look real quick. Okay, so I got rid of 31 and 35.
Can't stop there. You gotta go to the even number now.
No, that's it.
Uh,
If I touch it again, I'm adding one.